Good morning, all. Is my screen visible?
Yes, sir.
Okay. Now, wait a minute. So, as per our syllabus, after background, we have to see what is a digital image representation. And this part we have already finished in the introduction lecture. How image is being visible. It's like I will start from here, and I will explain while going ahead. As I said, these are the books that we can refer for this subject. Gonzalez and Wood's digital image processing. Also, we can use AK Jain. Few other books are listed here. If you are interested, you can go ahead and have a look into that. This is how that Gonzalez and Wood's book look like. This is actually second edition. You may also find third edition also. So under visible spectrum, we can have images, and visible spectrum means in a range of frequencies those are generated. The frequencies with wavelength varying from 4 nanometer to 7 nanometer. It's called as a visible light, 4 nanometer to 7 nanometer. So, if that visible light is incident on the eye, or I can capture and I can analyze that data, that signal, and it will be perceived by our brain as an image. So these are some popular applications where image processing comes into picture. The first diagram is a circuit board controller, and as you can see, very minute details of that circuit board are available on this image. And this image can be further processed to analyze whether there are any link break in the PCB. This kind of image can be used if the medicine or the tablet packet is completely filled or not. If there is any missing tablet, or if there is unfilled tablet or broken tablet, then those kind of uh, filled packet will be rejected. This is another application where image processing is used to check whether the bottles are completely filled or not. If the bottle is not completely filled, then such kind of bottle will be rejected. This is an image where the image processing is used to see if there are air bubbles in the clear plastic product. If there are air bubbles in the plastic product, that will be very delicate and it will be rejected. And few other applications such as cereal and intracolor implant. So in many other applications we use image processing. And as I said, in the visible spectrum, when the light is incident on an object, suppose this is an object, when the light is incident on that object and the reflected light reaches to human eye, when reflected light reaches to human eye, then that light will be perceived by human brain through eye, and it will be analyzed as an image. So these are a few other applications where uh, thumbprint can be uh, examined, or the fingerprints can be used for the image processing, and fingerprints can be used for the attendance monitoring or the secure entry, etc. And you can see lower two images are for the automated license plate reading. As you can see, this is the actual license plate. As you can see, the image which is captured in a dark light. Image is captured in a dark light, but the number plate part is highlighted and it has made bright by using the image processing tools, and from there some kind of techniques are applied so that the license number plate can be identified. That is this. The same can be seen here in the lower one example. And these are few other applications where the human being, suppose this is a human being, by using some image processing, we can identify the actual part or the actual boundaries where the human is standing. And with further processing or enhancement, we can further refine the result and we can get the actual data like this. So even if the human portion of a human being is in the darker shades, still it can be easily detected by using some image processing enhancements. And the same can be true for this lower one application. The actual position of these two human beings, which is not so accurately detected with the lower end processing. With further enhancement, we can identify the actual person. So, so what basically is a digital image processing? Digital image processing has three different uh, uh, sections in which you can process an image. The first part is a lower level processing, where we use the image processing to generally remove noise and sharpen the image boundaries or to blur the image so that some kind of noise will be less pronounced. In mid-level processing, we identify some kind of objects such as how we identified the number plate in the previous example. That is called as mid-level of image processing. Identify some kind of attributes from an image. For example, if I give you an image of a particular bird song, how the audio of that bird song looks like. Suppose this is how the audio of particular bird song looks like. By using this image, you can identify which bird is it. So suppose it is a crow. It is a crow, then its image will look like this. Suppose if it is a sparrow, the bird song of sparrow will look different. And suppose for the quail, it will look different, and so on. So by looking at the image of that particular bird song, we can identify the species of that bird. This is mid-level processing, and in high-level processing, it needs a kind of machine learning to identify the scene and take the automated action. So in kind of autonomous navigations, for example, uh, live traffic monitoring by using Google Live Location that uses the cameras to identify the crowded areas on the road, and the GPS navigator tells us that which road is busy and which road is non-busy, and accordingly we can select a route and we can proceed to the destination. So here some kind of intelligent programming is needed, and that is called as a high level processing of an image. Okay. So basically, the elements of a image processing we have already learned, but let's let's just have a look at what are the different elements involved in the digital image processing. Though these are not so important from the syllabus point of view, but it is necessary just to have understanding of the rest of the topic. So in the element, let me open this module one to some other application. Let me open with Microsoft Edge. Elements of image processing. So as you can see here, we have a computer. This is a main building block. Uh, with this computer, we have a image displays, such as a monitor on which we can see that image, digital image. We have a mass storage where we can store that image. We have specialized image processing hardware, such as any other hardware which can enhance the image. We can have softwares built in that computer to process that image. We can have a printer to print and to generate the hard copy of that image. And to get a image, suppose from this side we are getting an image and we are storing to the computer. So to get an image, we need image sensors. So this part, image sensors and specialized image processing hardware, these two are actually part of a camera. I hope you understand. So this side, some image is available or some scene is available. You are capturing that scene. You are applying some brightness control or say focus and ISO and many other things through a camera. So this sensor and specialized hardware, these two collectively is a camera, and that image is given to the computer, which will be further processed or stored into the computer, and it can be used as per the requirement. And that computer is connected to the network over which we can send that image to some other computer, or we can receive images from some other computer. Okay, so I don't think we need to discuss all of these blocks separately, because everyone knows how computer monitor is displaying a number of things, and how computer performs tasks, how mass storage stores the data as one byte is stored at one address. So this is just an overview. So we see that image sensor is with reference to sensing, two elements are required to acquire digital image. The first is the physical device that is sensitive to the energy radiated by the object, and second is image processing hardware. So we will be talking about this again in the later course. So let's just have a idea that there will be a sensor on which, if the light is incident, suppose light is incident from this side, then this sensor will have a property that depending on the intensity of light, suppose this light intensity is 1, here light intensity is 2, and here light intensity is 12. So depending on the light intensity, the particular part on that sensor will generate the electrons, and that means the device which is used here, this device is photosensitive device, and it senses the amount of light incident on it and accordingly generates the electrons. Okay, and those electrons will be collected from the back side of this particular image sensing device, and that will become an image. Okay, so it will give some kind of matrix like this. And here, when where light incident is 1, the matrix value will be less. Here the light incident is more, the matrix value will be more, and here the matrix value will be in between 1 and 12, that is 2. So depending on kind of image sensing device is used, the number of levels that will be observed in this matrix will vary. So if you are using a high resolution device, the number of levels will be more. If you're using a poor quality device, the number of resolution or number of levels in that matrix will be less. Specialized hardware means the camera in which you have some other additional features, such as zoom in and zoom out of a lens, then ISO control, shutter uh, speed control, and so on. Computer also, we know what computer is, we know what software is. So I'm not wasting time here. We know what mass storage is. Image display unit, that means monitor, that also we know. Hard copy devices such as maybe it can be a printer, inkjet printer, or it can be a CD-ROM device in which we store the data and we can carry it anywhere. And in a networking, the computer is connected to uh, any other devices in the network. So we saw now what is the element, what are the elements of a digital image processing. Now we will see what are the fundamental steps in image processing. Okay, so we saw what are the elements. Now we'll see what are the key stages or fundamental steps in a digital image processing. So as you see here, from the left side, we have a problem domain, that is a scene which is to be captured or scene which is to be processed. Then we will have an image acquisition, where the image or digital image will be formed using that scene. Then it will be enhanced. Enhanced means it will be modified in such a way that it will look more better and more application oriented. Then restoration of the image, morphological processing. We will see what all these blocks mean one by one. Okay. So as I said, first part, as it is highlighted here, it is the image acquisition. So as I said earlier, we will have some kind of sensor. So suppose light is generated from the source. It may be sun, or it may be other man-made source such as tungsten filament light or tube light or any other. So from this source, a light is generated and it is incident on the scene. So let's consider this is a scene element. What is shown here is a scene element. On this, light is incident, and the reflected light is uh, incident on the imaging system. Imaging system means basically the image sensor on which the digital images form. So as you can see on the back side, uh, uh, the individual elements are available. So as you can see, this is a one element. This is another element. This is another element. So every square box is one element. And as I said earlier, the smallest possible element in an image is called as a pixel. Okay. So here, this image sensor will be generating small elements called as pixels, corresponding to intensity of light falling on it. So suppose this is your sensing device, and suppose this part is illuminated with bright white light, this part is illuminated with dark black light, this is bright white light, and this is some in between, let's say gray level. So the image will be formed, and in this image, some of the pixels in the left top corner will be black, some of the pixels in the lower part will be sorry, bright white means these pixels will be white, these pixels will be black, and these pixels will be in between white and black, some gray level. So we will have different intensities here. As I considered only three light intensities, we will have only three intensity levels here. But in actual scene, the amount of intensity or the number of intensity levels will be more, and hence the number of intensities level observed in this image also will be more. Now it depends on how many bits we are using to represent the image. Again, we will be talking about this later course. But by now you remember one thing. Suppose if I use only one bit to represent the image, 0 will represent a black color, 1 will represent a white color. So with one bit, I can use only two intensities, total black, total white, right? If I use two bits to represent the color intensity or the brightness level, then I can represent 00 complete black, 01 little darker shade, 10 little brighter shade, and 11 total bright or white shade. So with two bits, I can represent four intensity levels. If I keep going, and if I use 8 bits, then I can use 2 raised to 8 number of intensity levels. If I use 16 bits, I can represent 2 raised to 16 number of intensity levels. And as the number of intensity level increases, the image will look more and more smooth. And the image will look more closer to the actual scenery. I hope you understand that. So in an image acquisition, each individual element will be represented by some kind of intensity level. So if you see here, the actual scenery is very smooth and very uh, good looking. But if you see the image formed by that, it has the different intensity levels which are easily recognizable, or we can easily identify that there are variations in the intensity. There is no smooth variations, there are sharp variations, and which are annoying, which are not looking good. Instead, if I use, now suppose, let me zoom in this part. Let me zoom in this part. Okay. Suppose I have this as a 1 pixel. Instead of this, if I have smaller pixels, let me divide that 1 pixel into 4 different pixels. Then what will happen? Then each of the intensity levels which are shown here will be represented by 4 different intensity levels. So there is a chance that we can smooth the color intensity like how we see here in the actual image. So as the number of intensity levels increases, or number of pixels in image increases, we can get more and more better image. So here comes the concept of resolution. There are two different types of resolutions. One where the number of pixels are increased to make the image more smooth. This is called as spatial resolution. Spatial means in a space coordinate we are increasing the number of pixels. And the another resolution is where we use the larger number of bits to represent the more number of intensity levels. And this way we will get the better resolution. This is called as tonal resolution, where the picture tone or the brightness tones are increased, and hence it's called as tonal resolution. See, whatever I am saying now is just for the brief introduction, and you don't have to worry much about it because we are going to discuss that again in depth in the coming lectures. So this is first part, image acquisition. So once I acquire the image, now what I have individual pixels, each represented by some number of bits, and it is stored in the memory. Okay, so in a memory, I will have a matrix. That matrix will have number of values, say 10, 20, 30, 40, and each of that value 10, 20, 30, 40 will be stored in the storage by using some number of bits defined by the resolution quality. So let's say we are using 8 bits to store the single pixel. Okay, then image enhancement. As you can see here, we have one image here. Does it look good? No, it does not look good because the picture looks slightly dull because the intensity or the contrast is not good. The contrast means uh, the difference between brightest and darkest color available in the image. And here, as you can see, brightest and darkest colors are not so separated out. They are very close to each other, and hence this image looks dull. But as compared to this, if you see the same image which is enhanced means what? Some kind of processing is done on that image so that it looks better. And after that enhancement, with even naked eyes, we can easily identify which part of that image is a beams and which part of that image is a some darker background or shadow. So this is called as an image enhancement. These kind of image enhancements are necessary in the prior stage so that the brightness levels in the image will be maintained, or the histogram of the image. Let me clarify later what histogram is. But instead, I can say to make the good contrast of the image, this kind of histogram, this kind of image enhancement techniques are necessary. Then the third stage is image restoration. So this is a satellite image taken from some satellite, and as you can see, there is some kind of mat-like structure or some uh, horizontal and vertical lines, as you can see if you closely look at that picture. This is because the moving satellite in the space and also moving earth. So maybe this image can be enhanced to look better, but in that case what will happen, these horizontal and vertical lines also will be enhanced. So only image enhancement is not sufficient in such kind of images where you have a lot of noise, horizontal and vertical lines, or this kind of dot, this kind of dot. These are called as black and white dots. These are called as salt and pepper noise. So the image which has this kind of salt and pepper noise, white and black dots, or horizontal and vertical lines cannot be processed directly by using image enhancement. We need to do image restoration. So in that case, what is done is some kind of mathematical algorithms are used to remove the horizontal and vertical lines because they are generated because of the uh, angular or linear motion of the satellite and earth, and that angular and linear motion is repeated with some fixed duration. That means there is some mathematical reasoning behind these lines. So if we can find out what is the relationship and how these lines are appearing, after what duration or after what distance they are appearing, if we can mathematically relate that, we can remove that also, isn't it? So this kind of mathematical algorithms are used to restore the image, and you can look at the next image, which is restored one. The horizontal and vertical lines are completely removed. So this image is not only restored, but it is also enhanced, because restoration stage follows the enhancement stage. First it is enhanced, then it is restored, and then it looks like this. So the key stages of a digital image processing: first we saw the problem domain, that is the actual scene. Then we will acquire that image by using the camera. It has the sensor, it generates the uh, digital image, which is kind of a matrix. Each matrix data or each matrix number is stored with by finite number of bits, and then it is enhanced, and then it is restored. After restoration, we have morphological processing. So at this stage, you won't understand what morphological processing is, but you can think of like having a letter. Okay, if I write Rahul like this, now as you can see here, if I apply the digital image processing to identify the name, then to identify the name, I should first separate all the letters, individual letters from this image, and I should compare each individual letter with the um, stored stored pure quality letters or alphabets from A to Z. So if I want to compare this first letter, I should first separate out this R, and then I should compare with the stored values of A to Z, and then when it matches, I will identify that yes, this is the letter R. Before doing that, I should separate them. So as you can see, let me write that little bolder so that you can see. Now I'm sketching that same R again. So what basically you see here is, when this kind of text is used to write names or any other text, what you see here is when the text R and A is separated, there the line is little thinner as compared to the actual R and actual A. Here the line is somewhat thinner, isn't it? This is somewhat thin. This part is somewhat thin. So if I use some kind of morphological processing means you can thin the data or you can thicken the data. So thinning means, see what, how R looks here and how R looks here. I can imagine as if I have operated morphological thickening operation on this. So the earlier R is a thin R. I have thickened it and now it looks like this. Okay. So this kind of operations can be used. So now what I can say is, if I apply morphological thinning operation on this some 2-3 times, then what will happen? The line which is little oh, narrow, that will completely disappear and I will get R and A like this. So this part which was narrow, that got completely removed because I applied morphological thinning operation again and again on the text. And then I can easily use segmentation. See, after morphological processing, what I'm doing, I'm using segmentation to segment or to separate out letters which are not connected. So R is a separate letter, A is a separate letter, and this part is called as a segmentation. Because I want to analyze what the text is, so I have to apply morphological operations such as thickening or thinning operation, so as to make the uh, letters disconnect, and then I can apply the segmentation to extract individual letter, and then I can use object recognition. Object recognition means after segmenting, you compare it with the stored values of A to Z to identify what is that, and then you will get that it is the R. After recognition, you will show on the screen that it is the R. So while showing on the screen, you will have to use the letter R, which is not same as what is written here. This written R is different, and what is displayed on the screen of a monitor is different. So what is written here is maybe in a Times New Roman and some 12 font, and what is written here is a handwritten R. So the representation and description means you represent that analyzed data by using a stored values. So you have stored values of A to Z, and you use those stored values to reproduce the R, which is actually uh, RAHUL, which will be printed in a nice, good font and a nice size. Okay. So I explained morphological processing. Here you can see some examples. This is a some minus sign with some circle and then B. This is dilation operation. That means which is same as thinning operation. So as you can see, this is the image on which I am applying the thinning operation, and this is the image which is obtained after the thinning operation. You can see another image here. I have applied A plus B, that means thickening operation. I will explain these operations when we'll go ahead with the morphological processing, but by now you just remember one thing. On the same image, when I apply thinning, it looks like this. When I apply thickening, it looks like this. So this image is not good because there are broken lines. This image is also not good because there are much wider lines, and those are almost touching each other. But if you compare with respect to original image, this image is a very good image because there are no thick lines as well as no discontinuous lines as compared to the this one. So as per requirement, we have to use thinning and thickening operations or dilation and erosion operations, which are collectively called as morphological processing. Then segmentation. Segmentation, as I explained earlier, I want to separate individual R, A, H, U, and N. That is called as a segmentation. So here in this image, you can have a look at this particular image. It has shadows, so you can see this part is a shadow, this part is a shadow, and here also some part is shadow. You can very easily observe that there are shadows. So I want to separate out my actual object from those shadows, and that is called as segmentation, as I said earlier, right? So if you see the brightness level is very high for the background, darkness is very high for the object, and a little less darkness is available for shadow. So if you remove this part which is little less darker by using some kind of processing, then what you get is this. So as you can see in this image, there are no shadows. So we have successfully segmented that spanner. This is actually an image of a ring spanner which is used for mechanical uh, operations. So there are no shadows anymore, and we have separated the image from the shadow. This is called as segmentation. And as I said earlier in the previous example, after separating out the letter R, we have to analyze and identify what is this R, or what is this, whether this is A, B, C, D, or whether it is R, and that is called as object recognition. So here also, after segmentation, we have to compare this image with a lot of other object images, and then we have to make decision that yes, this is a spanner. Okay, so that is called as object recognition. So in object recognition, what we have to do, we have to compare that image with rest of the images, and that image will match more with the spanner images, and hence we can make the decision that yes, it is a spanner. So we will see later what how to do that, but by now we are just understanding the stages. Then last is to represent the image, as I have already given the example. I separated R, then object recognition stage. I identified that it is the R, and then I want to reproduce the R on the image. Sorry, on the display unit. So I represented that R on the display unit by using dis, uh, some processing. Additionally, we have color image processing and image compression steps involved in the image processing, which are not necessarily following the path that we understood. This is a path which has a sequence very important: acquisition, then enhancement, then restoration, then morphological, then segmentation. See, what will happen if I try to do the segmentation? What will happen if I try to do segmentation before morphological processing? As I showed you in the previous example, here as R and A is connected, segmentation will become difficult. On what basis will you segment? Here, in this case, we can segment on the basis of the image part which is not connected to each other. Let's segment that as an individual letter. But here, everything is connected. How can you segment? Isn't it? So you can segment, but that will be very complicated, and depending on any other application, it will become more and more complicated. So the complexity level will be very high if you try to segment without using morphological processing, or if you interchange the sequence of segmentation and morphological processing. If you do segmentation earlier, then morphological processing will be of no use, right? So these steps or this path is very important. First, to do this, then you need to do this, and then this, and then this, and then this. So as I said, additionally we use image compression and color image processing. So image compression we will learn later, but you know what image compression is. Image compression means the storage requirement of an image will be high, so we'll need to reduce the storage requirement while maintaining the quality. I want to reduce the storage requirement while maintaining the quality, and that is called as image compression. I told you in the introduction lecture that there are two types of image compressions. One where the image is compressed but the quality is kept maintained, where compression will be very less. With little amount we can reduce the space, and other where the image is compressed with a larger amount, more space is saved, but the quality of image will be degraded. So first of this is called as a lossless compression, and another example that I gave you is called as lossy compression, because you lose the information content from that image. And in color image processing, we use same kind of task, but individually we operate on a red, green, and blue color levels. We individually operate on a R, G, and B levels. So as you can see here, this is the uh, image which is processed by using color image processing, and you can identify the different levels of uh, heat in the image. So the cooler part is shown by using green color, uh, and hot part is shown by using blue color. Lesser hot is shown by the red, and then yellow, and so on. So we use this kind of processing. So again, I have shown the image acquisition process that I showed you in the beginning, in the little zoomed in version. As you can see, each individual pixel is shown by one single color. So within a pixel, color intensity cannot change. Please remember this thing. Within a pixel, the color intensity cannot change. But from pixel to pixel, it can change. From one pixel to next pixel, it can vary. But inside a single pixel, only one color intensity will be available, either white or black or any gray level. So look at this, if you look at this, there will be only one color intensity everywhere. In every box, there will be only one single color intensity. Okay, so we will see um, remaining part like elements of visual perception and how image is formed, how image formation model is uh, available, and all those things. We will see this in the next lecture. Anyone has any doubt in this current lecture? Please unmute and ask whether you understood. Whether you understood. Okay. Okay, Sujit, thank you. So we will leave now, and we will meet back again in the next lecture tomorrow at 11:50. Thank you.